Hello. I wanted to take a minute to go through the activity from lesson 1.2. How many pairs of shoes do you own? This is our lesson for section 1.2, which is displaying quantitative data with graphs. So I have jotted down here the numbers that were shared to the class through the survey that was taken at the beginning of the semester and the other day. And what I need you to do is to take those numbers and enter them into Statsmedic to create a dot plot, a stem plot, a histogram, all three of those. And then you're going to sketch those in the area for number 3. In order to be able to do that, of course, you need to decide if this data is categorical or quantitative. And just a reminder, categorical data is data that is given by values that are labels or names, while quantitative data is numerical data that would make sense to average. So would it make sense to talk about the average number of pairs of shoes that are owned by students in class? And that would make sense because it would tell us about the most common value or a likely value for how many pairs of shoes a student randomly chosen from class would have. So this is quantitative data, which means you are going to use the Statsmedic app for one set of quantitative data, one group, and one variable. So go ahead and take a moment, pause the video, and enter that information into Statsmedic, and then we will take a look at the information that you gathered. Okay, so these are the 3 representations of the data that you are going to get out of Statsmedic. There is one more called a box and whisker plot or a box plot. We're going to talk about that tomorrow, but we have our dot plot, which is this one right here. We have the stem plot, which is right here. That's also known as a stem and leaf plot. And then we have the histogram. So the next thing that we want to do when we look at quantitative data is talk about what the data shows us, how we could describe the distribution based on the shape, if it has any outliers and what they are, the center of the data, and how variable the data is. And by variability, we're going to talk about how spread out the numbers are within the sets of data. Or within the set of data. So we're going to start with shape. And you can really look at any of these 3 graphs to kind of get an idea about the shape of the data. Most of the time we're going to be given, or many times we're going to be given a histogram. And this histogram, if you look at it, it goes kind of up really quickly, and then it comes back down a little slower, and it has this long tail that comes out. Okay, we only had one piece of data over here. It was 35 pairs of shoes. This kind of shape for data is called skewed because we have a peak and then a long tail in one direction. Now, if that tail is to the right or on the positive side with larger numbers, then that is skewed right. If the tail is to the left, to the lower numbers, then that is skewed left. If it doesn't have a tail and it seems to be pretty even on either side, that would be symmetric. And if we have data that is consistently all about the same height, that is called uniform data. So this would definitely be data that is skewed to the right. It's just, we want to kind of describe how skewed it is. Like, does it look like this and then like have a super long tail, or does it just go up a little bit and then have kind of a stretch that's a little shorter? So we want to use LY words when we describe how skewed or symmetric data is. Is it slightly, moderately, fairly, or significantly. Those would be your most common. Slightly, moderately, fairly, or significantly. And I would say this data is fairly skewed right, okay? We do notice in our dot plot that not only is it skewed right, but it also has two peaks that are about the same, that are the same height, because we've got this peak of 4 and this peak of 4 here. We don't notice that in our histogram, we just see one peak. We also don't notice it in the stem plot. And with your stem plot, you have to imagine that you're going to take that picture that you're given and you would think about like rotating it, okay? That's how you're going to get that picture of whether it's skewed or not, is if you rotate it, then we can see that the data goes up and then has a tail, okay? So obviously we don't plot our stem plot that way. We plot it horizontally. But when you think about it, you want to think about these numbers being on a number line, in which direction it would go. So this is fairly skewed right. The next thing that we want to look at is, are there any outliers, or do there appear to be any outliers? So when we're taking a look at outliers, we will eventually have a rule for determining if a value is an outlier or not. At this point, we're kind of just gauging it as best we can based on where the data is and where the rest of the data points lie. And in this case, you may look at this and think that the 35 is an outlier because there's this large gap between it and the other numbers. And that's pretty much the best reasoning we have at this point until we get a rule in place. So we would say, because we're not verifying it yet, the best way that we could summarize this right now with the information that we know and the rules that we're given is that there appears to be an outlier at 35, okay? Next up, we're gonna look at our center of our data. And the center of our data is exactly what it sounds like. It's kind of where the data is centered, what it kind of hovers around. And so you can get a feel for this by looking at the data. It's kind of the middle point, the balancing point, if you will, of your data. So it would be like right there, or in this one, maybe around right there. So that's kind of what you're looking at, is the balance point. And the two values that we use to describe the center are called the mean and the median. And you've probably heard of both of these. So you can choose which one you want to use. And if you go back and you look at your Statlet data, you actually have a box of summary statistics. We will have a rule for when to use mean and when to use median. At this point in time, you could choose either one. I'm going to go ahead and give my center of data by using the median. So I'm going to say that the median number of pairs of shoes is 10. And so I want to specify which measure of center I'm using and what that value is. And notice I've also thrown in there this context of pairs of shoes. We need to do that at least once as we work through the description of the distribution. You need to always include context at some point in your description of the distribution. All right, and then the last question, the last thing we need to address is the variability in the data. And so that describes how spread out our values are. And right now we really only have one measurement that we're familiar with that does that, and that is the range, which tells us how far it is from the lowest point to the highest point. We don't want to know specifically the lowest point and the highest point. We don't want to give this value as an interval. We want to give it as a numerical number that is the difference between the highest and the lowest. So our low point is 3 and our high point is 35. And so therefore our variability, our range, we would describe as, we could say, the number of pairs of shoes owned has a range of 32. And note, I did put the interval in parentheses. That's okay if you feel like you really need it, but you don't have to have that. Okay, you can leave it with just the difference. All right, so this is what we've got. Now, the next thing that I want you to think about is the three types of displays and why you might choose to use one over the other. So just think about it for a minute, maybe pause and brainstorm. What are some advantages? What are some disadvantages to each of these types of displays before I give you some ideas? Okay, so as you looked at these three types, I'm not sure what you might have thought about as far as advantages, disadvantages, what you like about one or the other. Um, but some of the things that you want to keep in mind here are just the ease of creating the graph and the information that it gives us and what it can tell us versus what the other graphs tell us. So all of three types have good things and bad things about them. The dot plot and the stem plot both are really nice because they give us a picture of all of the individual data points. We can see every point and what its value is. But if we had a lot of data points to plot, that could become very long and tedious, which is why we usually use a histogram when we have a lot of data. The disadvantage to a histogram is we lose those individual specific data points. It makes it harder to calculate values like our median and our mean and our range. So we can't be as specific and when we're describing the data as we could with one of the other two. But it is a lot easier to create when we have a lot of data. Okay, let's move on. And what you're going to do on this next part is we're going to compare two distributions. So I now have a set of data for you here. This is another set of numbers, and this is describing the number of pairs of shoes owned by teachers. And we want to compare teachers and how many shoes they own to students and how many shoes they own. So what I would recommend that you do is go to Statsmedic, copy the data that you already entered, and then hit the back button and go to the quantitative data, one variable quantitative data with multiple groups, and then paste your data into one of the rows of your table, label that students, type these numbers into the other row and label that teachers, and then we're going to compare the two. So after you've done that, come back. You need to copy one of those three displays, either the dot plots, a side-by-side stem plot, or the histograms into the section that you have on number 8. Only one. Okay, I'm going to put all three of these on my chart. So here's my histograms. Here is my back-to-back stem plot. Notice teachers are on one side, students are on the other, and here are my dot plots stacked up. Whenever you stack dot plots, you always want the scales to be exactly the same. Back-to-back stem plots, those are pretty straightforward. You're using the same stem with values on both sides. And same thing with the histogram. As far as our scales go, we want those scales to be aligned so that we can make really good comparisons. So as we look to compare these distributions, we're going to do the same thing we did before. We're going to compare their shapes. We're going to compare their outliers, if they have any, the centers of the data, and the variability in the data. Now, a couple important things to remember when you're making comparisons. You don't want to just list the features of each distribution individually. You want to make sure that you are comparing them using comparative words like more, less, greater, lesser, higher, lower, things like that. Okay, so which one has a higher center? Which one has more variability? Are they both skewed right, or is one slightly more skewed than the other? That sort of thing. So go ahead and give that a shot. Why don't you go through those 4 pieces of information to try to compare these two distributions, and then I will give you my summary and you can compare and see how you did. Okay, so when comparing these, we can discuss the shape, and both distributions for students and teachers are fairly skewed right. However, the student data appears to be slightly more skewed right than the teachers, just because it kind of has a longer tail. The peak is a little further away from the tail end, and it's a little taller, but that's because you have more data points. If we had the same number of data points for teachers, it would probably change the comparison a little bit. As far as the outliers go, we thought that there was an outlier for the students. It's not as clear if there's an outlier for the teachers, because we do have some larger values up here, but they're closer. Like we have these ones that are in the middle, so we don't really know. Is this an outlier? I mean, it's really far, just as far away from the chunk of data as this one was from this chunk of data, but these points in the middle make it a little bit more unclear if it's an outlier or not. So we're just going to go with there appears to be an outlier but within the student data of 35, but there doesn't really appear to be an outlier for teacher data. When we learn our rule for calculating outliers, that will be more clear. The center of data, again, since you ran these through Statlet, you can use your median or your mean. Our median for teachers is 12.5 versus a median of 10 for students. So we want to make sure we talk about how there's a higher center, a larger value for the center of data, which means in general that teachers have more shoes than students. And then the variability is slightly greater for students than it is for teachers because they have a larger range, which is all that we can use right now for the comparison of variability. So a greater range means more variability. All right, so I'm going to go ahead and go back through, and we are going to review some of the key concepts, things that you want to make sure that you cover and do as you're working with quantitative data. So on the first page of this, we always want to make sure that we include our labels and a key when we're creating our graphs. We want to use words that have ly at the end whenever we're describing especially our shape or how skewed the distribution is, or how symmetric the distribution is. Always throw in those ly words. These four phrases, shapes, outlier, center, and variability, are the four things that you have to discuss when describing a quantitative distribution. So right now, the acronym for that is SOCV with how they have it listed. Your book is going to teach it as SOCS, shape, outlier, center, spread, instead of variability. And I am going to put it as SUCS in your big ideas, shapes, unusual features, which includes outliers, the center, and the spread. So I like SOCS as an acronym, but I think when we use SOCS and we talk about just outliers, we have a tendency to forget that there's anything that is unusual. If there's anything that's unusual about a distribution, we need to include it. For instance, if you have a set of data about the ages of people at a movie theater, you might have a group of really young kids and a group of older kids, or a group of older adults is what I meant to say. So you might have a cluster of data here and a cluster of data here. So we would talk about how there's two clusters with gap in between. That's unusual. So that would have to be addressed in that second step of unusual features. So just remember that describing quantitative data sucks. So we have to hit all four of those: shapes, unusual features, center, spread. And it sucks that we always have to use context, okay? So always include context. So I did that twice here: pairs of shoes owned. You only have to do it once. You can't do it too much, but you have to include it somewhere. All right, then on the second page, the other thing that I want to talk about is what I mentioned before. Whenever you're comparing two distributions, always, always, always use comparative language. Things like, let me see if I can find some and highlight them for you. Both distributions, I mean, that talks about both of them being the same, slightly more than the other, With outliers, you kind of just do list them, but you might want to say like one has an outlier and the other one doesn't, or one has an unusual feature, the other does not. Higher center, more variability, greater range, that sort of thing. Those are all of our comparative words that we want to make sure that we include all along the way. So we're not just listing and describing two distributions, we're really truly comparing them to one another. All right, last up, our big ideas for this section is a lot of what I've already said. When we describe distributions, we want to make sure that we use context and that we're using ly words along the way to describe. That just means that we don't want to specifically say that something is symmetric. Most data, hardly any data unless it's created that way, is perfectly symmetric. So we would say it's fairly symmetric, that something is slightly skewed right, those sorts of things, okay? Then our shapes, unusual features, center and spread. Shape could be, like I said, skewed right or left, symmetric, uniform, that's where we use those ly words. And then we can also discuss whether data is unimodal or bimodal. It's going to be assumed that it is unimodal if you do not say otherwise. Bimodal would mean that we have two peaks within our data, kind of like we did on the dot plot on the student data, because there was 2 peaks of 4. So we could call that bimodal. We lose that feature if we look at the histogram. Unusual features, outliers, gaps, clusters, multiple clusters, things like that. The center of data would be the mean or the median. And then the last one, S, is our spread or variability. Right now, all we have is range. We're going to add a couple more tomorrow when we start talking about how we describe quantitative data with graphs. And then, of course, like I said at the end there, always have comparative words when we have 2 or more distributions that we are discussing. So this is your big ideas. Make sure you do the check for understanding and the homework.